This is lesson 8, and we are going to be moving fairly fast. And I'd like to remind us that we have to go step by step. As I said before, you should not skip any of the presentations I've made before. You must follow the lectures in sequence so that you are able to understand the next lesson. We have had a test already that was timed online, and we anticipate to have another test to cover the remaining lesson 8, which will focus on plant breeding. This is in respect of the prospective learning outcome for us to understand the breeding strategies of important crops. This diagram is a bit crowded, but extremely important. I will shortly be giving an assignment based on this diagram for you to write up a report in place of the individual presentations you would have done. Therefore, you study this very, very carefully. I like also to mention that the part we are going to concern ourselves on begins with the consideration of this lower part. Everything we've done right from where we started with needs assessment towards the desired features here at the very end of maintenance methods, we've really been focusing on the aspects of pre-breeding. So with a very short summary, I'll be making some comments on pre-breeding. But what we will particularly want to concentrate on is what I want you to remember using this mnemonic gender PM. And this is after the issues of pre-breeding that we've talked about. The gender part here, the GER, is generative methods, and they involve crossing the G in the gender, the generative methods. They entail crossing. Then the DER, gender, is derivative methods, and they involve selection, including evaluation, of course, and we shall see how evaluation comes in. Then P stands for plant biotechnology, where we're talking about the molecular assisted selection, genomic, genotyping by sequencing, called GBS, the GWAS, genome-wide association studies. Therefore, the word gender PM is the complex part that we should really derive the message from for the lesson 8. very critical lesson. If we miss it, then we will have missed the whole intent of plant breeding course or module. So M stands for the maintenance methods. All right, coming from there, I would very quickly want to put your mind back to where we just came from in lessons 7A and 7B, that when we're talking about bell-shaped curve, and you've seen that on your test, a bell-shaped curve addresses the issue of variance or variation across given accession genotypes or phenotypes, if you like. And that variation is translated into statistical variance, which when you have sufficient population, or at least a population that assumes the normality assumptions, then we have the left tail and we have the right tail. That the tails on the central tendency, where the cluster, where the population mu or mean is called the property of dispersion. And therefore, a parental generation assumed to be normally distributed in a bell-shaped curve is where we select parents to cross. And when we select these parents to cross, and we actually go ahead to cross them, we will expect a baby bell-shaped curve. The baby or the offspring will constitute a normally distributed population, because the selection, after we've selected the plants, the parents, will have variance as well. And we talked about the concept of variance, covariance, correlation, regression. That's the message you got, and that's what was on the test that you concluded just the day before. Then out of that, we pointed out the importance of QTLs and pointed out the importance of heritability, R, the selection response, which involves looking at the selection response and the selection differential for that matter. We talked about that, and it's just a review to throw our minds back. The selection differential was given by this example, which you should look at one more time and get to understand that in it, we have a formula of this kind, which involves the selection intensity, the accuracy, the genetic standard deviation, which is more or less the genetic additive effects, and then we have the generation interval, which is a complete generation cycle. And as you can see in this formula, the selection intensity is a value expressed as K. And as we increase the intensity, we see that the value of K correspondingly increases. Important message to know. We already talked about this because it takes us into the breeder's equation. And in this way, we said that heritability in the narrow sense represents the proportion of phenotypic variation due to additive genetic effects. Hope you understand that. Hope you can give some thought to it carefully as you study. Also, we said that the S is the consequence of the product of selection intensity. Again, I repeat, the consequence of the product of selection intensity and selection accuracy combined, which is multiplied by heritability. So these bell-shaped curves are where we always will consider a best population at a respective generation cycle. And as it is, we are interested in the rate of genetic gain, rate of genetic gain, rate of genetic gain. Because here breeders aim for that rate of genetic gain, without which progress towards successful selection would be meaningless. So the rate of genetic gain is the rate of the speed of a given vehicle that will end up at a destination. The destination is a new variety. We already have reached a destination when we talk about a new cultivar. Therefore, the rate of genetic gain really applies to the breeder as a driver toward the progress of achieving a new variety, which is the destination. So understand this. The rate of genetic gain is the speed at which there is a meaningful gain in the selection response as breeders progress to the ultimate, to the end, which is a new variety. And so that's how you have to understand the issue of the parental generation, where we get the selected parents, and then we have the offsprings that reflect a bell-shaped curve. Remember, when we're doing the crosses between two parents, we're not going to just settle on one plant. I used to think that F1 was just one plant. It's several offsprings that when you self the F1, you're getting a variance that has a population mean, or sample mean for that matter, and standard deviations on either ends of the central tendency. So here, the breeder's favorite equation is extremely important, as we said, and you'll see how it works into our issues of what we are going to be talking about. All right. I would like to indicate here that pre-breeding is all those things you have done. It is a must pre-step to plant breeding. It refers to all activities that are designed to identify desirable characteristics. Remember in your test, I did ask, what is the other word for trait property? It is characteristic. And or genes from unadapted materials that cannot be used directly in breeding populations. We need to actually transfer such genes from unadapted materials of course, those desirable ones into the trait determining genes or alleles that are desired. So really, it is transferring from the unadapted germplasm brought to core into intermediate set of materials. And it is really the intermediate set of materials from which the breeders begin to use for producing new varieties for farmers. Therefore, pre-breeding is a necessary first step in the use of the diversity that has arisen from the wild relatives or other unimproved materials. Therefore, the activities are a collaboration between the germplasm curator, the people who keep the germplasm, and the plant breeder who needs to work with the curator, the germ or the gene bank manager, so that both are able to understand the scope and value of germplasm collections and how new traits from these collections can be bred into new varieties. So the adoption, not adaptation, the adoption of pre-breeding facilities or the pre-breeding intermediate materials will facilitate the efficiency and effectiveness of the real crop improvement program that follows. That's why accessing the genetic variations conserved in gene banks is extremely crucial. And that's where, even at the gene bank stage, students can be sent there, researchers can be sent there to undertake pre-breeding studies. So the decision to do pre-breeding is based on the expected efficiency and efficacy or effectiveness of finally moving the target traits into cultivars for farmers by breeders. Therefore, pre-breeding is a must. It is a necessary step if desired genes are available. And here, if they are available at the gene bank, are available in the gene bank accessions, they may not be there. In fact, they may not be even well adapted to the target environment. And therefore, the plant breeding may or plant breeder may have to actually acquisition some of the existing elite varieties from other breeders if they allow that further breeding, for example, suitable for Namibia, can be done. Because a plant breeder seed to be released to another breeder requires some conformity to patent laws or intellectual property or IP policy, because plant breeder seed may be protected. Or one could actually mine or extract desirable genes or alleles from wild species that may have been easily crossed with a crop species. Or even getting it from more distant wild species, which are more difficult to cross. And this can be done through molecular procedures to get desirable alleles there or a desirable gene from there. So basically, the major applications of pre-breeding in crop improvement involve broadening the genetic base to reduce vulnerability. Remember, used to say many times before that you have variety genetic breakdown. Well, genetic breakdown doesn't happen. Of course, one can look at it in terms of genetic drift, but really, when we have not broadened a genetic base in the new cultivar that we desire to have, then it becomes vulnerable to abiotic and biotic stresses. So the other major application of pre-breeding in crop improvement is we move the genes, as we've said before, that really, when we have the intermediaries, then it is the most effective strategy to pre-breed. Pre-breeding may not apply to all cases because such studies may have been already done with a breeder elsewhere. And so here we can say, sometimes when we are bringing the new varieties in, we identify traits in such exotic materials, and then we move them into genes. We move the genes into materials that we want to be adapted to Namibian environment. Remember, we said you can define plant breeding as adapting variety to an environment, adapting. And of course, identification and transfer of novel genes from unrelated species using genetic transformation techniques, again, from materials that are actually obtained from pre-breeding studies. There are challenges. There are challenges for applications of pre-breeding in crop improvement. And that's why you can see in the figure that we will be displaying, which indicates that we may have lack of characterization and evaluation data, may have lack of it, or may not have been sufficiently characterized and evaluated. Then we may have knowledge of genetic diversity being fairly limited, and then we may also have a lack of interspecies relationships known. So here, for example, the Namibia Gene Bank, we may probably find that the accessions in that bank, gene bank, may be limited by a high degree of difficulty and the length of time often associated with separating the desirable genes from undesirable ones. So if we ask from materials from there, we have really the unknown, the undiscovered range of the variation, some which may be good, may be ugly, may be probably okay for use. So here, we know that through plant breeding, through pre-breeding, a plant breeder will then have best the identification of the germplasm by collecting information on phenotypes, family relationships, and the genotypes. Such information may be necessary to make ready a start of having the best accessions for breeding. So we shall stop here for this bit that involves prebreeding and deal with it in the next lesson. So please put this in mind as we will be moving into the next lesson. Thank you.